The DBW is a year-long speaker series funded by NSF for the advancement of detectors. Today's talk is being given by Dr. Martin Itzler. Dr. Itzler is CEO now and also CTO at Princeton Lightwave, a company which develops single photon detectors for multiple applications. Dr. Itzler got his PhD at Penn and then went to Harvard as a postdoc, and he's been at Princeton Lightwave for 8 years or so. And Dr. Itzler is going to be talking about single photon APDs, particularly in gas, and introducing Dr. Itzler.
Great. Don, thanks very much for the introduction. Thanks very much for the invitation to participate in the workshop. It's a pleasure to be here. Thanks for all of you for joining in. What I'm going to talk about today is work that we've been doing, and I'll try and touch on work done by many others in the field, doing photon counting with indium gallium arsenide phosphide single photon avalanche photodetectors. And just before I get started, I want to acknowledge both my colleagues at Princeton Lightwave, as well as quite a number of colleagues and collaborators from around the world who are working in this field. And in many cases, these are folks who have provided extremely valuable feedback on the performance of these detectors, and they've done quite a lot of characterization on our avalanche photodiodes. So here's an outline of what I'm hoping to cover in the workshop. I'll give a little bit of motivation in terms of applications and drivers for these kinds of detectors. And then I'll talk a bit about the fundamentals of how these devices work and what some of the most important performance parameters are. And then I'm really going to try and cover 3 of the trends that I see going on today in this field. The first area is getting photon counting with these detectors at much higher rates than have been available. There are challenges to counting at very high rates. Sorry. Okay. There are a number of challenges to counting at very high photon flux coming into these detectors, and I'll talk a little bit about those, and then I'll try and summarize some of the progress that's been made in that area. The second trend that I'd like to talk a bit about is the advent of free-running operation with self-quenching versions of these single photon avalanche diodes that we refer to as negative feedback avalanche diodes. And I'll talk a little bit about the integration of this feedback and then the self-quenching mechanisms. And then the third trend that I'll try and cover a little bit about is the scaling of these detectors to large format arrays. And this becomes critical for various applications involving different kinds of imaging. And then I'll sum up with what I believe are some of the future prospects in using these kinds of detectors in various ways, and I'll try and give maybe some hints about where I see things possibly going. So in terms of motivation, high rate photon counting is extremely important in anything that looks like communications. And really, I'll point out 2 areas. One is exploiting the quantum mechanical nature of photons for quantum information processing. And generally, the faster you can process, the more desirable it is. Another area is more classical communications, but where you're using photons, and generally the driver is to do communications over very long-range distances. And of course, again, photon arrival rate should be as high as possible to enable as fast the transmission of information as possible. There are other cases where you're not dealing in a communications domain. You don't really have any knowledge about when a photon will arrive. It's not synchronous with some system clock. And so in these asynchronous applications, what you really like is single photon detectors that are free running, that can be armed and ready to count a photon whenever it arrives, register that count, and then very quickly rearm. LiDAR measurements over long distances to do Earth science is one example. NASA is a big user of these kinds of detectors. Also, very many kinds of fluorescence measurements based on time-correlated single photon counting also are targeted at measuring temporally random single photon emissions, and that's where having free-running performance is quite important. And then finally, in terms of why you'd want to scale to large format arrays, in some ways it's quite obvious. You'd like to have single photon sensitive pixels in lots of different kinds of photon-starred low light level imaging applications. So certainly astronomy and astrophysics are classic examples of this. Night vision imaging is a very important potential for these devices. And then I'll talk a little bit more about three-dimensional LiDAR, or laser radar imaging, where every single pixel makes a time-of-flight measurement. So that gives you the third dimension that gets added to your otherwise typical two-dimensional image from a matrix of, or an array of pixels. And using that information, you can generate 3D images of objects in the distance. And just as an example of how this 3D LiDAR mapping has been used, this is pioneering work that's been done by MIT Lincoln Laboratory, and I should mention that really that organization has done pioneering work on all of these single photon or so-called Geiger mode APD devices. And these are examples of images that were captured in Haiti after the earthquake in January of 2010, where they were able to get a tremendous amount of detail about damage that occurred throughout the country and the state of the infrastructure there, and to do all kinds of mapping aerially to get a tremendous amount of information very quickly, but in great detail because it's three-dimensional data. Okay, so let me move on to some of the basics of how these detectors work. So the basic premise of an avalanche photodiode is that I absorb a photon in the absorption region that's sensitive to the wavelength of interest. Photons get absorbed here. Carriers get created and are then injected into a multiplication region that's at sufficiently high electric field that the impact ionization effect gives you an avalanche of charge, and hence the name avalanche photodiodes. And so the key is to have a low but finite field in this absorber so that you collect the carriers quickly, and then a high enough field to give this avalanche. And the structure that we use is one that's actually been widely deployed for telecom receivers. It's a diffused buried junction based on zinc diffusion into the indium phosphide cap region I show here. And it's very stable and very reliable. It's a tremendously good platform to build, for instance, these high yield arrays with very uniform pixel response. But these devices are rather different than their telecom equivalents, and really they had to be completely re-engineered to do single photon counting. So just to make that distinction a little more clear, this is an IV characteristic for a standard linear mode APD. The dark current here shows low sub-nanoamp value up until a so-called breakdown voltage, where the avalanche process basically runs away and you get an enormous current beyond that breakdown voltage. And in the meantime, with light incident on the device, you have this linear gain region. The reason these are referred to as linear mode APDs is because the photocurrent out of the device is linearly proportional to the amount of optical input coming into it. And it's really a purely analog response. Now, the Geiger mode version, or single photon version of this device, actually entails biasing this device above its breakdown voltage. And so what you've done is you put the device into a metastable state where a single carrier coming into the multiplication region can generate an avalanche of charge. And so what I show here is this process of arming the device, waiting until a photon arrives and generates a carrier. The carrier is then injected into the avalanche region, and so an avalanche occurs, and that generates essentially a macroscopic pulse of current that allows you to detect the single photon that came into the detector. And then it's necessary to quench that avalanche, by bringing the voltage back down to the level of the breakdown voltage by some means, and then you rearm the device and you start the whole cycle again. And so what you have is you have a device that really is a photon-activated switch. It's not strictly correct to talk about the gain of a single photon or Geiger mode APD, although what you really can talk about is an effective gain where if I look at how much charge is created in each of these avalanches, essentially that's the amount of gain. One photon giving me all of these charges you can talk about as being the effective gain. But that's something that's determined by not only the device itself, but also the circuitry that comes behind the device, and I'll say more about that. Okay, and so in terms of the trends in counting single photons with avalanche photodiodes, I should point out that there has been quite a lot of work to try and get to the single photon sensitive level with linear mode APDs. Now, generally the problem is with a linear mode APD, you need a lot more gain than those devices are usually operated at. For telecommunications receivers, those devices have a gain of maybe just 10 or 20. You need gains of at least, let's say, 1,000 or even 10,000 to easily detect a photon. And so the Geiger mode way of operating the device is terrific for generating lots of charge. In fact, the problem with the Geiger mode devices is that we really have too much gain because there are other negative effects that come from having so much charge flow in the response to a single photon. And these are effects, the primary one is referred to as after pulsing, and I'll talk more about that. Crosstalk between the pixels is another problem. And so the trend is that for Geiger mode APDs, we need less gain. And I think that probably you've got a convergence of the linear mode and the Geiger mode devices to some optimal gain, and I'm just going to put a guess that maybe about 10,000 charges is the right amount. And so now if we look at this basic behavior of a single photon detector in terms of detecting photons as they're arriving, the ideal performance is that if a photon comes in, the detector registers it and gives you an output. If a photon doesn't come in, then there's no output. That's what you'd really like. Always see a photon when it arrives, never see a photon if it doesn't arrive. Now, you do have events, though, that violate that ideal condition. In the first case, I could get a photon but not get an avalanche from the detector, and so I've missed that photon. On the other hand, even in the absence of a photon arrival, it's possible that the detector generates an avalanche, and that's a so-called dark count or false count. And so these phenomena really define the photon detection efficiency. That's the probability that a photon causes an avalanche, and the dark count rate, the probability that the detector gives me a count, gives me an avalanche, even in the absence of a photon. Now, in addition to those two really fundamental performance parameters, there are other cases where you care about the accuracy of the detector in timing that arrival. And so how much randomness there is in the avalanche relative to when the photon arrives is referred to as the timing jitter. What you'd really like is a detector that tells you exactly when the photon arrived, and there's going to be some level of inaccuracy to that time measurement. After pulsing is an effect where the dark count rate increases following a previous detection, and I'll talk more about where that effect comes from. But I just want to make the point also that, as often is the case when working with these kinds of semiconductor devices, there are various sorts of trade-offs that need to be managed. You can improve the photon detection efficiency and the timing jitter by increasing the amount of electric field across the device, by increasing the voltage, but then you get an increase in the dark count rate as well, which is better. I can look at decreasing the temperature to reduce the dark count rate, but then the after pulsing becomes more of a problem. So getting the ideal device design involves managing a lot of these different trade-offs, and very often they depend on what the application demands. So to say a little bit more about where the detection efficiency comes from or what dictates it, really you're looking at the product of three probabilities. One, that when a photon arrives at this absorbing material, what's the probability that I actually absorb the photon? And when I absorb the photon and generate an electron-hole pair, what's the probability that I collect the carrier that was generated that's going to start an avalanche in the multiplication region. And finally, then once I have a carrier in the multiplication region, what's the probability that it generates an avalanche which is big enough for the circuitry behind the detector to actually see? And so in a well-designed single photon APD, generally this absorption probability today is on the order of anywhere from, say, 70 to 90%. The collection efficiency, we believe, is extremely high, very close to 100%. And really, the big trade-off that happens in these devices is trying to get to a higher avalanche probability. Certainly, there are devices where we can be operating above 50% today, and so you can see that that would give you kind of a total detection probability of on the order of, say, 40, 45%. But that's the maximum at which devices generally operate today with acceptable dark count rate. Now, in terms of where that dark count rate comes from, there are two mechanisms that dominate the dark count rate in these structures. One is just the thermal excitation of carriers in this indium gallium arsenide phosphide region. It needs to be fairly narrow band gap in order to absorb the photons that we're trying to detect. We're working with wavelength ranges between 1 micron and 1.7 microns. And the other source of band counts is from the high electric field in the multiplication region, where the fields are high enough that there is a certain amount of tunneling that occurs in that indium phosphide material, and that can generate charges that were not photon initiated. And so in either of these mechanisms, what I get is a carrier injected into the multiplier that can generate an avalanche. And it didn't come from a photon, so that means it's giving me a false count. And so now if I look at the sort of state of the art in the trade-off between these two parameters, I can get higher detection efficiency by increasing the bias across the device, but that's also going to drive an increase in the dark count rate. And I should point out, the detection efficiency scale here is linear, but the dark count rate scale is logarithmic, and so there's an exponential increase in this dark count rate generally as you start to go to higher and higher detection efficiencies. In the meantime, though, the state-of-the-art performance for these devices is about 1,000 dark counts per second, or 1 kilohertz dark count rates for detection efficiencies of at least 25, 30%. And there's no reason that you can't go higher in detection efficiency. You put more bias than you can. The measurements made here just were limited to a finite excess bias, the bias above the breakdown voltage being only 4 volts. I also mentioned that one of the critical performance parameters is the timing jitter for many applications. These devices can be very fast. In fact, they're on a par with silicon versions of the silicon photon APDs, which have a jitter of about 50 picoseconds. Superconducting single photon detectors, nanowire detectors in particular, can reach as fast as 30 picoseconds or as little as 30 picoseconds for the timing jitter. Very often these values are dictated by the back-end circuitry. And so with well-designed circuitry, there have been demonstrations showing that we can have sub 50 picosecond timing jitter with these devices. And there are a number of contributors having to do with where the photon is absorbed and whether the carriers that get created get hung up at various interfaces in the structure. But really the dominant contribution comes from the amount of time and the variability in the avalanche building up to the level that you can detect. So let me now move on to the first of those three basic applications where I've seen a lot of progress occurring and where there's been a lot of focus, and that is trying to count at very high rates. Now, there are really two essential challenges when you move to high rate photon counting. One is the fact that we're arming the device by putting this bias above the breakdown voltage, and we're trying to do that arming very fast, and so you get high frequency transients in that case. It's a common artifact for any sort of high bandwidth signal modulation. The second problem is suppressing the so-called after pulses. This is the case where you get dark counts that are correlated to the previous detection of a photon, and I'll describe where that comes from. They can be mitigated by basically leaving the detector unarmed for a sufficiently long period of time, but then what that does is it slows down your counting rate. So that's just not a viable approach when you're trying to count at high rates. I'll also point out that you do have to be concerned about the intrinsic bandwidth of the device, but that's not a problem for small area, small diameter versions of these detectors on the order of 25, 30 microns. You can certainly support at least gigahertz scale counting rates with these devices. So, just to make this point about the transients causing problems, if I'm trying to raise the voltage on the device to put it in its armed state in a very short period of time, let's say on the order of 100 picoseconds, then because the device is reactive, in particular the diode has a capacitance, you get a transient response that winds up causing lots of confusion in figuring out, did you see an avalanche or not, if you don't eliminate this transient. And so eliminating that has been a major focus of a lot of the work at high frequencies. And a lot of the strategies involve creating an identical version of this transient and then subtracting it from the output signal. And that's done in various ways, and I'll show you a couple of those later. If you think about the ways that you could modulate this voltage in order to put the device in its armed state, you sort of see that if you have this very high slew rate, sort of quasi-rectangular wave type gating of the device, there are lots of frequencies involved here, and that's what gives rise to those transients and that ringing phenomenon. Now, it turns out that if you apply a bias to this device at a very high frequency, but just one frequency, you gate it with a sine wave, you can get rid of that sine wave quite easily. And that was a clever trick that was demonstrated 5 or 6 years ago by researchers at Nihon University, and has been shown elsewhere. And what's really nice about this is you have no harmonics, so you just filter at that frequency that you're gating at, and I'll show what happens in that case. And then finally, I'll talk about some devices where we've been looking at self-quenching, and there, if you think about it, really you're just putting a DC bias on the device, and that's all you ever do. And any response you see is from the avalanche itself. There are no transients at all in that case. Now, I mentioned the afterpulsing as being a key problem. Here, what I'm showing is that if you gate the device too quickly, then you find that you fill a certain number of traps, defect sites in the multiplication region of the device. And now you have to wait for those carriers that got stuck at these sites to come out of it. And so that detrapping can trigger additional avalanches if you arm the device too quickly. Now, there's a way to get around that. You just use a long hold-off time to not arm the device until all the carriers have been detrapped. But as I pointed out before, that winds up slowing down your counting rate. And so there are several strategies for overcoming this afterpulsing. Using long hold-off times is just not viable because it gives you too low a repetition rate. You can try and reduce the defects that cause this trapping in the first place, but in fact that's a rather hard problem. And to date, really, people have not made a substantial amount of progress there. You could try and intentionally kick the carriers out of those traps, and people have tried using sub-band gap photons to sort of get rid of those carriers with lower energy photons. So far, those efforts have not been successful. And so really the key technique that has been used to date is to reduce the amount of charge that flows with each avalanche. The reasoning is the amount of carriers that get trapped is proportional to how much charge is in each avalanche. So if I reduce the amount of charge in each avalanche, I'll trap less carriers, and with less trapped carriers, I get lower afterpulse. Now, one way to get less trapping or less charge flow per avalanche is to use very short gates, and fortunately, that's consistent with high-speed gating. Okay, I'm gonna skip a little bit of the material on the afterpulsing. The basic point here is that we can measure, as a function of time following an initial avalanche, how long did it take or what was the probability that an afterpulse occurred given waiting a certain amount of time. And what we see is that the longer you wait, the lower the probability that there's a carrier being detrapped. And to find the total afterpulse probability, really what you need to do is sum up over all of these probabilities. So, at very, very short times after the avalanche, this is just 20 nanoseconds, for instance, Here you see that there's about a 1% probability of an afterpulse. That drops down to 0.1% by a few hundred nanoseconds. And so you're dominated by afterpulsing in these short time frames. Okay. And if you go back and you ask, well, can identify what these defects are that cause the afterpulsing, if you go and look at the literature on defects in indium phosphide, in fact, you find a wide range, a big spectrum of different trap sites. And so it's really a tough problem to understand what's causing these. And I don't see a lot of progress in the materials challenges in the near term. And so it looks like there are going to have to be clever approaches to deal with this afterpulsing with the number of defects that exist in the device today. Now, there's an interesting question as to whether these defects that cause the afterpulsing might be related to the dark count rate. If you recall, I mentioned that dark counts come from both thermal generation in the absorber and tunneling in the multiplication region. And it turns out, if you get enough data, and we've been taking this data over several years with devices that are in production, so they're very, very similar, and they're measured with exactly the same technique, what we find is that there is a pretty good correlation between how much afterpulsing you get and what the dark count probability is. It suggests that the traps in this multiplication region that give rise to the tunneling effects that create dark counts may also be involved in the afterpulsing. And while it doesn't tell us any detail about where those traps come from, it does give you a fairly useful prescription for how to get low afterpulsing detectors. It says use the very lowest dark count rate detector that you can get. The other rather useful phenomenological result of these studies in afterpulsing is that the shorter the gate is, the lower the afterpulsing. And it's not just that using a shorter gate gives you a shorter time window for the afterpulsing to occur in. Using a shorter gate also gives you less avalanche charge. And if you remember, I pointed out that reducing that charge is key to trapping fewer carriers and then getting less consequent afterpulsing. And so reducing your gate by a fairly modest factor here, by 30%, winds up giving you a 2.5 times decrease in afterpulsing. And I give examples of, for instance, data taken by the group at NIST that has shown similar things where there's a very, very big impact in reduction of afterpulsing using shorter gates. Okay, and so as the very last elements on high rate counting, I just want to show, first of all, that over about the last 13, 14 years, there's been a tremendous increase in the demonstrated gating rate for how fast people are able to operate these devices now. I'll show you a couple of examples up in the gigahertz. And, you know, not surprisingly, we're lagging behind the state of the art in the lab. You know, the Pentium always did as well. And so we're trying to increase this slope to catch up, but the basic message is that we've got about an order of magnitude a little more in terms of hitting the state of the art. Now, I think the more interesting question is, where can this go? And there may be fundamental reasons why this several gigahertz rate is starting to saturate where you can go in terms of the speed of counting with a single detector. This shows an example of the kind of technique that we use at Princeton Lightwave for counting at modestly high frequencies. This is the 50 to 100 megahertz rate, where you're using essentially a scheme that has two matched delay lines, and one is inverting and one is non-inverting. And at the output, they cancel the transients so that when there's no photon present, that you get a fairly nice flat background, and that allows you to see the small signal coming from a photon arrival. You can see if you had these kinds of transients where the photon arrives, you'd never see it. And in the meantime, you can now get rid of these transients by just gating them out temporally and amplify the small photon signal, and that's how you can do this detection at reasonably high rates. Now, there have been big increases in the rate by taking a clever variant of that kind of cancellation, where the group at Toshiba in the UK uses gigahertz rate. They're actually up to 2 gigahertz in terms of how fast they're gating their SPAD with a sine wave. And this is the kind of transient response you get when you just gate that device without any photon arrival. So what they do is they shift this entire signal by one clock cycle, by one period of this gate, and then they subtract the shifted signal so that it cancels out almost all of the transient, because the transient from one cycle to the next is virtually identical. And that allows them to see very, very small avalanches right on top of what remains of the residual noise coming from that cancellation process. And so that's been used to get after pulsing down to the level of 5% or less for at least 10 to 15% detection efficiencies, which are quite good for quantum communications. And all of this is done at a 2 gigahertz rate. Another example of this very high counting rate is in using sine waves. I pointed out before, if you have just a single frequency that's gating the device, then it's possible at the output signal to just filter out, using a very good notch filter, that one frequency. That means that there's nothing left of the gate signal, no transients, and all that you see now is if a photon arrives, you get a pulse, you get all the content at other frequencies, and so that again allows you to pull out these fairly weak photon-induced avalanches up at very, very high rates by getting rid of the transients using the sine wave technique. Okay, so I'm going to move on to the second of these major trends that I've described. And here, the idea is you can get those very high rate counting techniques to work, and they can mitigate after pulsing, but they've got the complexity of having those very high frequency driving signals. And so the question is there a way to actually operate the device without having to use all that back-end circuitry? And so what we've been looking at is trying to make devices that self-quench. And the simplest concept is, imagine that I've got the single photon avalanche photodiode, and now I put a resistor in series with it. When there's no current flowing in this device, that is in the absence of an avalanche, any applied bias basically is just dropped across the diode. It's basically used to charge up the capacitance of the diode. But once an avalanche starts, when a photon comes in and initiates that avalanche process, now I've got a current flowing. The current flowing through the resistor causes an IR drop, and that subtracts potential from the diode itself. And if there's a big enough drop in the voltage across this resistor, then essentially you can force the diode to reach the point where it's going to self-quench. So we've done this by integrating thin film resistors on top of our legacy structure, and just from an equivalent circuit point of view, this part in blue here is the SPAD itself. The load resistance of that negative feedback element is really the operational element of importance here. And in designing these types of devices, you have a key trade-off. You'd like to have a large resistance in order to promote very fast quenching and keep very, very little current flow going through the device. But the problem is that with a large resistance here, when you're going to rearm the device, which it does by itself, there's just a fixed applied bias across here. So an avalanche occurs, you momentarily drop voltage across the load, the avalanche quenches, but then you need to recharge the capacitance of the avalanche photodiode, and you have a recharge time constant that's the product, given by the product of this load resistance and the diode capacitance. And so the problem today is that those time constants are on the order of, say, 10 to 100 nanoseconds. That's really one of the big challenges of using these devices. But at any rate, when you go and you make a device like this, I mean, our first generation, showed that it's really nice in order to run this device. All you need is a bias T that allows you to inject your DC bias through this inductor and just count high frequency pulses through this capacitive output. And so this is a time snapshot of the kind of series of dart counts you would get from this device. And so if you go and blow one of these up, you see that you got about a few nanosecond type response time. And it takes a little bit longer for that current to die out. That's because this feedback is too low. If we go to a larger feedback, then we find we can get very nice, couple of nanosecond wide pulses that drop very quickly. And we also find that the amount of charge in this each avalanche is really reduced dramatically from the traditional ways of operating these devices. I mentioned that for reducing after pulsing, you'd like to get this charge flow smaller. I mentioned an optimal gain of, let's say, on the order of 10 to the 4. We're already down to somewhere in the mid 10 to the 5s, and so we've got about an order of magnitude to go. Now, if you ask how reproducible are the properties in terms of, say this peak height or the amount of charge in the avalanche. Then here I'm just showing some of the statistics. Basically, the standard deviation for the variation of the amount of charge per photon, or those peak heights, is about 0.28 times, it's about 28% of the mean number of electrons. So as I'll show you, this has implications for whether you can add together signals from multiple detectors. And it is possible, and I'll show you how that works. Okay. Now the third topic that I want to get to is the scaling of these discrete detectors to large arrays. And this is primarily driven by image applications, although I'll show you it also has implications for counting at high rates. This is kind of a schematic of the way that you would make a typical focal plane array that incorporates an array of these single photon APDs, and this is bonded to a readout integrated circuit that has appropriate electronics for running each of the pixels, each of the APDs in the array. And to increase the fill factor, we have a micro lens array on top. And then this whole thing is packaged into a hermetic housing, and we had a thermoelectric cooler to give modest amounts of cooling. And so this is just a photograph of the entire focal plane assembled without the lid. And we've taken this focal plane and now commercialized it into a fully turnkey camera, where essentially the camera does everything that's needed to run a 32 by 32 format array up to about 200 kilohertz frame rate. So this camera really can operate very, very fast, even though the format is smaller than standard cameras today. We can make up for that with the high frame rate. And so just to give an example of what the performance is like from those arrays, they've come a long way in the last half a dozen years. We can now make arrays of these 32 by 32 formats where every single pixel is in spec. There are no bad pixels in this entire array. This is a map of the entire 32 by 32 for dark count rate and for detection efficiency. And so these are now extremely useful for those, in particular, those 3D LiDAR imaging applications that I mentioned earlier in the talk. These arrays have been designed for 1.06 microns. The performance of the pixels is quite consistent. The dark count rates across the whole array are within about a factor of 2. And the standard deviation on the detection efficiency at a detection efficiency of 39% is about 6%. And we've seen that we can also make arrays that have substantially lower dark count rates. Here, the average dark count rate is only 2 kilohertz at almost 40% detection efficiency. And really, this is modest cooling. This is only minus 20 degrees centigrade, and so you could improve that dark count rate with further cooling. So in addition to those arrays at 1.06 microns, we've also made versions that are sensitive out to, in fact, almost 1.7 microns. These are generally for use with lasers at 1.5 microns for doing LiDAR or LiDAR measurements. We're also working on larger formats. We have 32 by 128 formats. I show a map of the dark count rate. There is somewhat more variation now because of the larger dimension of this detector, but again, we can get for these 4,096 detectors, we can get every single detector, or all but a handful of the detectors operating within spec on this array. I should also mention that as I said earlier, MIT Lincoln Laboratory has done pioneering work in this area. And just to give a feel for what the state of the art is, they have made arrays as large as 64 by 256 in this material system. Okay. And one last point to make is, all of the parameters I've been talking about are for single photon detection. So for instance, the detection efficiency is just what's the probability of seeing a single photon. If you're working in applications where, in fact, you have a few photons per pulse coming into a single pixel, your ability to detect that pulse is actually much, much higher. And so by the time you have just 5 photons per pulse, whereas for a single photon you might have only had a detection efficiency in the low 30% or 35%, you have over 80% detection efficiency for a pulse with 5 photons, and for detecting 10 photons at a time, you're up in the high 90%. Okay, and one last challenge that comes up in the SPADs I'll mention because I think it's the key challenge going forward. That's that every time you have an avalanche, it turns out that a very, very small number of photons are emitted by these hot electrons that are being accelerated in this avalanche. And so if those photons can get absorbed in neighboring pixels, they'll cause an optical crosstalk. And so this is one of the biggest challenges to trying to shrink the spacing between the pixels. Okay, so let me just now kind of move towards finishing up with future prospects. I mentioned the Toshiba technique for sort of doing the subtraction of one cycle from the cycle that just came before it, the so-called self-differencing technique. They've used this technique to show that, in fact, you can detect photon arrivals that are as close together as just 2 nanoseconds. So already you're at half a gigahertz in terms of not just the gating rate, but the actual detection frequency. And that's quite impressive. It says these detectors really can respond very, very quickly at the gigahertz level. In terms of how much higher that could go, you will run into problems now as you try to get up to, say, the 10 gigahertz rate. First of all, timing jitter becomes an issue. 100 picosecond timing jitter really is already gonna kill you if you're trying to count at 10 gigahertz and you need resolution on when the photon arrives. You have other inherent bandwidth challenges. In fact, even for telecom applications today, there are no APDs beyond 10 gigahertz in this material system. And so those kinds of limitations will probably keep you from moving beyond that rate. And I think really the prospect for counting at higher rates involves multiplexing many detectors together. That's really the way we're going to move forward beyond the sort of several gigahertz type counting rates. Now, you can do that. I mean, here, if I've got 32 by 32, I've already got 1,000 detectors in parallel. If I have an optical beam coming in 1 photon at a time, but I spread it out over the entire array, I could now, have the way that our ROIC works. We have quarter nanosecond timing resolution. We could already get 4 gigahertz sort of effective counting rates here. That could be much higher, but of course there is a substantial overhead to using these focal plane arrays. Now, I mentioned that the negative feedback APDs will independently go through this whole cycle of arming, quenching, and then resetting. And they give reasonably consistent pulse responses. And so you might ask, gee, can I put a whole bunch of these in parallel? And in a lot of ways, this is really just a solid state equivalent to a microchannel plate photomultiplier. Here's one pore of a photomultiplier plate. And now if I imagine making a matrix of these single photon NFADs, then I can get it to behave just like a solid state photomultiplier. And so these are just very early stage measurements of, for instance, taking a rather small 4x4 matrix of these NFADs and looking at the response when I have about 3 photons on average arriving every time we fire a pulse at it. And those pulses are Poisson distributed, so you can model exactly what the response of the detector would be. This is the standard deviation of the response of the detector that I showed you earlier as measured by the statistics of the pulse responses. And we see that we get really a very nice fit to the spectrum we're measuring. Of course, it's a little noisy, but the overall behavior is described by the simulation quite well. And you can go in and see that, yeah, I've got the distinct pulses corresponding to 1 photon arrival, 2 photon arrivals, 3 photon arrivals, and we're starting to get some level of photon number resolution from these sorts of matrixed NFADs. Now, what does it take to do much better than that? Really, you'd like to see your photons a lot more clear. You'd like to see these numbers of photons more clearly. This is the simulation for a ratio of the standard deviation over the mean avalanche number of 28%. If you can knock that down to 10%, then really now you have very well resolved peaks separating, for instance, 1 photon from 2 photons. And this starts to get very interesting in terms of using solid-state detectors to do photon number resolution. And then, of course, you could imagine taking these sort of micropixelated collections, these matrices of a small number of NFADs, and putting them into a bigger array. If I can shrink the size here further, then really I can imagine kind of getting to a next generation imager where every pixel has photon number resolution and can count multiple photons, unlike the current detector arrays. One last point here in terms of photon number resolution, again, going back to work that the Toshiba group has done with their self-differencing circuit, I want to show you work that they did just in the last 3 or 4 years, where they've shown that, in fact, even from a single detector, you can resolve some degree of photon number from just a single detector. They've done this both in InGas and with silicon SPADs. And there's really not been a clear explanation of where this comes from, but I think most folks would agree that what's going on there is that they're able to quench the avalanche so quickly that they're actually seeing individual photons giving rise to these small filaments of avalanche before the avalanche fills the entire active area, this whole region. That's generally what you see when you use a Geiger mode APD. They're stopping the avalanches early enough that you can still see these individual filaments, and that's where the resolution is coming from to more than one photon. And really, you can think of making the matrix of NFADs in the same way. We're kind of defining exactly where these filaments are going to occur, and we can measure many of them at one time. And just as a final slide on where can you take the basic performance of these devices, some time ago we put together a comparison of silicon and indium gallium arsenide devices, and of course the indium gallium arsenide phosphide devices will always be at a disadvantage because they have a narrower band gap. They're trying to detect longer wavelength photons, so they're always going to have more dark count rates from thermal behavior. But if we kind of level the playing field by considering the performance at different temperatures, where really we've taken into account the difference in band gap for these two detectors, and so we look at the performance at these two temperatures, which kind of take out the band gap difference, then what you see is that the silicon devices have about a factor of 5 or so advantage in dark count rate, and they certainly do have less defects giving rise to after pulsing. Jitter is almost comparable. And so if you continue to work on the problems in the indium phosphide material system to make it just like silicon, then maybe that's the level of improvement you have. This factor of 5 or so in dark count rate, maybe an order of magnitude in after pulsing, but probably not more than that, unless you really think you can take indium phosphide to a level more advanced than silicon, and it's going to take time to catch up. Okay, so in terms of summing up, in terms of what lies ahead, I think I've pointed out that I think counting up to about 5 gigahertz with discrete detectors, at least 5 gigahertz gating rates would be possible today, but to get to even higher rates, we're really going to have to use multiplex solutions, many detectors in parallel. There's a lot of interesting possibility for this sort of quasi-analog behavior from the negative feedback devices when you put them in parallel, and if we can shrink all of those matrices into small enough lithographically defined entities, we can make reasonable sized pixels that have this analog behavior. The scaling to larger formats certainly is achievable. I don't see any fundamental reason why we can't get to megapixel type formats for these devices, although shrinking the pitch is probably going to be the much harder goal than adding more pixels because of the crosstalk between the nearby pixels. And finally, improving the basic parameters is rather difficult from a material system point of view. And so really I think that continued progress is going to come from these really smart design concepts that various people have used to get around the inherent problems with the materials. So that was what I had prepared for today. Thanks very much.
Okay, thanks, Mark, for an excellent talk. We have a couple questions that showed up in the little chat box, so I'll just repeat those. Anyone who wants to ask any further questions, just go ahead and type them in the chat box, and we'll also take some questions from the live audience here. So the first two questions are from me. One is, do you know what the dark count rate is at really cold temperatures? I guess less than -70, because you talked about -70, right? But what if it were to go down to 40 Kelvin or 50 Kelvin nitrogen?
Right. So the big challenge there is taking the temperature down will be extremely effective for negating the problems that you have. Let me get all the way back to my basics here. It'll negate all the problems you have with the thermal generation in this low band gap material. I wouldn't venture to guess a number off the top of my head, but I don't think it's impossible that you could get to sub-hertz type dark count rates taking the temperature low enough if this is the only mechanism. The problem with getting really low dark count rates at low temperature is that these tunneling effects that occur in the high field multiplication region are relatively temperature insensitive. They really depend on temperature only through the band gap. The band gap will increase as you get lower in temperature. That will decrease the tunneling somewhat, but it still could be a limiting problem. And so what you'd really like to do is see if you can optimize the design of these detectors, which really are designed to work on the order of 200 to 250 Kelvin, and to see if there are ways to design this device that are much more amenable to going down to sub-liquid nitrogen temperatures. And I think that is possible.
Okay, another question I had is, have you characterized photon self-emission? I asked that question before you had gotten to the graphic you were showing. But even after what you've said, do you have a good idea of the spectrum of the emission or the probability of a photon emission per unit charge?
There's been work done on that particular issue in a number of places. Again, MIT Lincoln Laboratory, in doing a lot of this work, has studied that spectrum where they do see a fairly large peak close to the indium phosphide band gap and then kind of a longer black body tail. In terms of the number of photons generated by these avalanches, the characterization that's been done shows probably one photon per, say, 100,000 to million carriers. 10 to the 5 to 10 to the 6 carriers will, on average, will generate one photon. So that's another reason why reducing the avalanche charge per avalanche is very good in these arrays because it reduces the crossing.
Right, that's what I was going to say. If you get down to 10,000, then it's much less than.
Exactly. Then you have the ability to perhaps pack these pixels much closer together without the crosstalk really becoming a problem.
Okay. The third question is from Stefan, who wants to know what kind of timing jitter can you expect at, say, a count rate of 100 megahertz?
At a count rate of 100 megahertz. So the timing jitter, let me just pull up that graph here, is really quite dependent on the excess bias. And so if you can push the bias up to, let's say, more than about 3.5 volts on this particular detector, and of course that dependence will change based on the device design, then you can be at sub-100 picosecond jitters, and where the circuit at least is not the, where the circuit is not the limitation, where this is really device limited. And you can see that the circuit that was used to make this measurement obviously allowed you to get down to 30 picosecond jitter at very, very high excess biases. Now the problem becomes, if you want to operate at 100 megahertz, and you don't want your afterpulsing to be a big problem, because that rate is starting to get high, that may limit where your overbias can go to. And so the same way it would limit your detection efficiency, it also limits your timing jitter to somewhat higher values. Right? Same way working at lower excess bias means I have to have lower detection efficiency. It also means I'm kind of in this region of the curve here. But I think that on the 100 picosecond scale is possible. The real problem becomes, what's the circuit going to limit you to? And many of the circuits used in operating these devices will generally give maybe a couple of 100 picosecond timing jitter.
Okay, that's it for the online questions. Kim had a question. I'll repeat it so people can hear it.
I saw a statistic that you had your avalanche current volume down to about 3 to 5 electrons. And I can't remember if that was for your asynchronous, your active quenching setup, or what you call the negative feedback kind of passive quenching setup. And so
Right.
it was your passive quenching.
Yeah, so it is, that's in the case of the negative feedback setup, and that's a case where, you know, the series resistance as the load on the diode itself is fairly large. This is already now half a mega ohm. And we've seen that the avalanches can be reasonably small once you get up to the sort of mega ohm scale on the feedback resistance. The penalty you pay is a longer time to recharge the device, right? And really that problem is summarized here where, you know, the device has a fixed DC bias across it. It'll start to recharge by itself, but if another avalanche occurs, it'll pulse again.
And you get those smaller peaks where you haven't had the time to recharge, and that affects your detectability, right?
That's exactly right. That if you don't have enough time to let the device recharge all the way, that if there's a carrier that comes into the multiplication region and generates another avalanche, then it's possible you cause the device to fire again, but in the meantime, as it's trying to travel up this curve and recharging, only when you get back up to the top here are you at your full detection efficiency. Everywhere else along here, it's more limited. I mean, in some ways, it's kind of like a built-in hold-off time, but it's really a complication because at any point in time, you don't know exactly what detection efficiency you're at, and that can be a big problem for some applications.
One last question. You had mentioned that you were looking at hot carrier photon emission rates of E⁵, E⁶. And if you only have 3 to 5 carriers participating in the avalanche, you're looking at, you know, 1, 10, 30 photons per avalanche. Does that affect how closely you could pack pixels of this type as opposed to the active quench type where you have a harder time controlling the volume?
Absolutely. So that's a very good point. You know, here with this crosstalk phenomenon, this is now detectors on a 100 micron pitch, and we've done work to try and limit the amount of crosstalk between the nearest neighbors with these sort of optical isolation trenches. But you know, you see that as you get further away from this pixel where the primary avalanche occurs, definitely the probability of crosstalk at any of these further outlying pixels gets lower, but you're still having the biggest problem right at the nearest neighbors. And yeah, here I would estimate that we could have quite a few times that 3 times 10 to the 5. We're probably, you know, anywhere from 3 to 10 times more charge in these avalanches. So absolutely, if you put those negative feedback devices into arrays, you could certainly hope to have a lower crosstalk in those cases.
Okay, any other questions? No? Okay, if there are any questions online, you can type them in. Okay, I think that's it. Let's thank Mark again.